And welcome back, students, to our lessons in programming arrays. Today we're going to discuss one of the most important topics here in arrays, which is that of sorting an array. So getting started, one of the standard algorithm developments when you're learning to code is being able to sort data. It's kind of one of those standard procedures, everybody goes through it. Data sorting is just one of the natural processes. Now in this lesson, we're going to be developing an algorithm in order to sort data in an array. So to start, we are going to define a method called sort that will sort a partially filled array of numbers. So there's order from smallest to largest. We're also going to look at a bubble sort, which is a more crude version. It's one of the easier versions, you could say, but it's just another algorithm. All right, and as I mentioned, we're going to look at the bubble sort and the selection sort. So let's start first with the bubble sort. This is often known as one of the simplest sorting algorithms, where an array is traversed from the first element to the last. So in the sort, the current element is compared with the next element. So let's say you have an array of 2, a very small array, is going to compare array at index 0 with array of index 1. If the current element is greater than the next element, it's going to swap it. So it's going to take whatever was in 1, move it to 0, and what was in 0, it's moving to 1. So the bubble sort example is provided in the class materials. All right, so let me just pop over here. So here's my bubble sort, and you can see it's a very simple algorithm. This is all it is. This is primarily right here, the bubble sort. So it takes in the array's length, and then what it does, it says for I is equal to 0, I is less than n minus 1, because it's got to do 1 less than the length. So remember the array, if you do it to the length value, you're going to get out of bounds error. So we have to take a 1 less than, because if you say array of length 5, the problem is if you look at the index at 5, it goes out of bounds. So I plus plus, then j is equal to 0, j is less than n minus 1, j plus plus. So what it does, it says if array of j is greater than the array of j plus 1, swap the temp and the array j values. So int temp is then set to the array j. Array of j is then set to j plus 1, so it's setting equal to the next array value. So it's whatever was in, let's say it's position 2 and 3, so whatever was in 3 is now in 2. And in order to put that number that was in 2 into 3, we set what was in 3 equal to that temp. So the temp variable kind of fulfills the role of holding on to whatever number is being switched around while the other one moves. Right? And here's just a simple print array method. So if we look at our demo here, here I'm creating an unsorted array and I'm printing it out, and then I call the bubble sort class and print out the sorted array. So here I say bubble sort array equals new bubble sort. Int bubble is equal to, here's a set of integers right here. Print out unsorted array, and then call the print array method to print this out. Of course, which we've seen print arrays before. It's simply just this right here. We've seen that multiple times. So if I run this class, all right, you can see unsorted, it's 64, 35, or excuse me, 34, 25, 12, 22, 11, and 90. After it sorts it, it is now 11, 12, 22, 25, 34, 64, 90. So it is now in order from smallest to largest. All right. Now, if you're curious to know how many times this is going through the loop, what I can do is I can come over here to my bubble sort here, and I can add in a public static, and we'll just make it an int, and we call it counter. Right. And what I'm going to do is inside of this loop here for the bubble sort algorithm, I'm just going to do counter plus plus. Right. And what that does is every time it makes a change, it's going to add 1 to the counter. And I'm just going to go here then, system.out.println. And if I just do a bubble sort dot counter, it should now print out how many times it took it to traverse that loop. So 14. So that means it made 14 changes in having to move those numbers. Okay, so let's keep that in mind as we traverse through our pieces here of information. So a bubble sort is always going to start back at the index of 0, right? Even if the items are sorted. And this is really kind of inefficient, right? Because if the smallest item is already at the end, why should you have to go and reject? Now, granted, if it goes in, that's only making a change if it has needed to move something, right? So it still is going to go through and just make those iterations, but it's going through the loop every time. If we actually look at the milliseconds time comparing the bubble sort to the selection sort, you would see a difference, right? So let's talk about the selection sort by sorting an array. All right, this procedure sort has one array parameter, which is A. Now the A parameter will be partially filled, so that if there's an additional form parameter called number used, which tells us how many array positions are used. Thus, the heading for the method sort will be public static void sort double array A int number used. The method sort rearranges the elements in array A so that after the method call is completed, the elements are sorted as follows. A of 0 is less than A of 1, which is less than or equal to A of 2, which is less than or equal to all the way up to A is less than number used minus 1. All right, the algorithm we're going to use to do the sorting is called selection sort. So you can see so far this is very similar to the bubble sort. Very similar. And it is actually one of the easier, more complex algorithms to understand. Obviously, bubble sort, pretty simple. You're just swapping numbers until you have them all smallest to largest. Here, this is another approach to being able to sort those numbers. So one way to design an algorithm, when you're just talking in general, is to rely on the definition of the problem. So what is that you're actually trying to solve? In this case, the problem is to sort an array from smallest to largest. And we already looked at how to do that with a bubble sort. All right, this means rearranging the values so that way A of 0 is the smallest, A of 1 is next, and so forth. That definition, of course, yields an outline for the selection sort algorithm. For int index equals 0, index is less than number used, index plus plus, place the index smallest element in A of index. Now, there are many ways to realize this general approach. Also, we already saw how to do this with a bubble sort, but now we're going to look at with a selection sort. Now, the details could be developed by using two arrays and copying the elements from one array to another in a sorted order, but using a one array should be both adequate and economical. So you actually could theoretically create one array that has your original values, create a second array, put the values into that second array in the sorted order, and then the second array would have them. But as we just pointed out, that's not ultimately what we're trying to do. It's kind of not really economical because it's creating a whole another array, and that's not what we want to do. All right. Therefore, our method sort uses only one array containing the values to be sorted. The method sort rearranges the values in the array A by interchanging pairs of values. So let's just talk about how the selection sort works, because obviously it's slightly different to a bubble sort, but it's similar. So consider the array on the following slide, which I'll look at here in a second. The selection sort algorithm will place the smallest value into A of 0. Okay, that makes sense so far. The smallest value is in A of 4. So the algorithm will then change the values of A of 0 and A of 4. The algorithm will then look for the next smallest element. The value of A of 0 is now the smallest element, so the next smallest element is the smallest of the remaining elements. A of 1, A of 2, A of 3, so forth, all the way up to A of 9. The next smallest element is A of 6, so the algorithm will then interchange the values of A1 and A6. So that's exactly what we have going on here. So here's my original algorithm here, original array, excuse me. So A of 0, you can see, is 8, and of course 3 was the smallest. So the first change it makes, it goes through and swaps these two. So it's pretty much inspecting the entire array rather than going element by element by element. All right, so swaps these two. So now 3 is here. So it knows that because 3 is now the smallest element there, I don't need to look at A of 0 again. I can go ahead and look at A of 1. So now I go to A of 1. Okay, well, that is at 6. So then checks the array again. Well, 5 is now the smallest value. So let's swap A of 1 with A of 6. all right? And that's going to give me 3, 5. Now it's going to keep doing that up until you fill the entire array that is sorted here. So 3, 5, 6, 8, 11, 12, 15, 17, 19, 28. All right, as we mentioned, the algorithm then positions the third smallest element and so forth. As the sorting proceeds, the beginning array elements are set equal to the correct sort values. So pretty much as the array is going along, sorting these things, it's sorting them from smallest to largest as it goes along. And the sorted portion of the array will continue to grow by adding elements one after the other from elements in the unsorted end of the array. Now you'll notice that with this algorithm, it does not need to do anything with the value of the last index variable, a of 9. So after it gets up to, sorts a of 8 with like a of 9, it can get to a of 9 and say, wait a minute, this is the last value in the array. Because all the other elements have been positioned correctly because they've all been sorted, a of 9 has to have this correct value because it's the last one. So after all, the correct value of a of 9 is the smallest value left to be moved, and the only value left to be moved is already an a of 9. So by the time it gets to that very last value in an array, that should be the last sorted value. So it really doesn't need to do anything with the last value. So that's why we can, when we look at the algorithm for that, we don't need to sort the final value. So let's talk a little bit about sort. In the definition of the method sort, it is shown in the class selection sort. The method index is smallest finds the index of the smallest element in the unsorted end of the array, and then it does an interchange to move this next smallest element down into the sorted pair of the array. The method interchange, which is also shown in selection sort, is used to interchange the values of the index variables. And so, for example, the following call would then interchange like a of 0 with a of 4, interchange 0, 4a. So before we get to comparing the two sorts, let's take a quick look at the selection sort. So here's my selection sort, and you can see right here is the sorting method right here. All right, so in here you can see we have a for loop again, but you'll notice that it is not a nested for loop. All right, bubble sorts is a nested for loop. And that's the easiest telltale sign when you know you have a bubble on your hand because it's a nested for. Here we only have one for loop. All right, and it says index of next smallest is equal to index of smallest, index a, number used, interchange index, index of smallest a. So if we look down here, index of smallest is right here. So it's using this and interchange. Index of smallest says index or int start index double array a int number used double min a start index int index of min equals start index int index for index is equal to start index plus 1 index is less than number used index plus plus. If a of index is less than min, min is then equal to a of index of min is equal to index. Right? And it goes ahead and sorts through that whole thing, return index of min, and you can see here is the actual interchange. So here, double temp, temp is equal to a of I is equal to a of j, j then it becomes temp. So this right here is kind of similar to like what we saw in the bubble sort. It's kind of a similar thing. But how we approach this is two totally different ways. Right? And of course, we just have our print array method here. If I look at my selection sort, you can see it's kind of a similar thing. We have an array. We're going to print out the contents before the sort and after sort. So if I run this one, you can see here's the array beforehand and afterwards. And it's sorted 3, 4.4, 5.5, 7.7, so on. Right. Now, like I said, very similar. However, it's slightly more complex because it's a more efficient algorithm. So let me just put in here, again, one of our public counter things. So public static int, counter? Right? And I want to do it so that way it does it every time it makes a change. Now, if I put it in here inside of the sort algorithm, counter plus plus, system.out.println, it'd be selection sort.counter. Run. You'll notice we have the value 9, which means that this algorithm only made 9 changes. Think about that. The bubble sort took 14 changes. The selection sort made 9 changes. And also look at the length of these arrays. this array length was 1, 2, 3, 4, 5, 6, 7 elements. If we look at this one, it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 elements. If I were to just, for example, shorten this up, so it's 1, 2, 3, 4, 5, 6, 7 elements. So I'm just going to cut these for a moment. I don't want to lose them. If I just cut these and make it so it's just these elements now, you can see now I've dropped down to 6 hops. So if they're the same length, you can see that now it's almost cut in half. And these are for very small arrays. Our arrays are very, very small here. Right? Imagine if we had arrays of, let's say, 50 elements, how much that would change in terms of the number of hops that it took for it to create those different iterations. So I'm just going to go back to our notes quick here. Let's talk about those two different sorts. Now, the bubble sort algorithm is a good algorithm for sorting an array that's pretty much regarded as almost sorted. So let's say you had an array of 10 elements. And of that array, let's say you had 7 out of 10 of those were in order. You just had maybe a couple mismatched somewhere in the middle. Everything else, though, is in order. For arrays like that, it's actually okay. All right. So if I go to, for example, go back to this array here, and let's just say I take and put these elements here and move them so they're here, and then run it again, you can see it jumped from 14 hops down to 5 hops just by changing the order. Because if you notice, by just moving where those 3 elements were in the array, it changed it so that way it's a lot shorter of a sort because it's already mostly sorted. 12, 22, okay, 11's not in order, so it's going to have to move that one. 6 here, okay, it's going to have to move that one. 34, 25, 90. So, like I said, it's mostly in order, so it shortens down the number of hops it has to do. Now, with bubble sort, it's not competitive with other sorting methods for most situations. All right? And the reason why we want to stress this is because if you're ever asked what's like one of the most inefficient sorting algorithms, it's a bubble sort. A bubble sort is one of the easiest ones to write. Very easy. 2 nested for loops. Boom, done. You don't necessarily have to clear your class. You can just do 2 nested for loops, sort the data. Life is good. However, it's not at all efficient. Now, a selection sort slightly improves over a bubble sort. It's not the best, right? But it is better than that of a bubble sort, as it's no longer going to check values that are already sorted. Remember, it sorts as it goes through. It's sorting the array. It's putting them in order. So after it puts the first value in A of 0, it does not need to come back and check A of 0. Right? Remember also that with a bubble sort, it's always starting back at index of 0. It's coming back to check A of 0 and see if anything changed with A of 0. The selection sort doesn't do that because it's automatically moved the smallest value down to the bottom. So if we're developing an algorithm for efficiency, a selection sort is going to be a much, much better approach than that of a bubble sort. All right, well, that concludes today's notes, folks. Obviously, it was a little bit of a longer one, but it's very, very important that you took away the pieces out of here. So until next time.